Welcome back to my lecture series on James space, a counterexample in functional analysis, or more precisely, in Banach space theory. Now, it is finally time to study the actual James space. Up until now, we have only done some preliminaries in Schauder-based theory and also constructed some tools that we will use later to embed J into its double dual space. So first up, we want to define James space. What is James space? James space is a subspace of C0, and it is exactly those sequences alpha n which in a specific norm, which we will define right now, this is finite. And the norm looks like this. This looks horrible. However, we can make this very much more tame by decomposing this norm into its different parts. And that is exactly what we are going to do now. So we will define that Z of a finite subsequence of alpha n will be exactly this term that you see up there. We have this large sum of all the alpha pn's minus alpha pn plus 1 plus alpha pm minus alpha p1 squared, and all of that in the square root. Now, this part does not belong to this sum anymore. And furthermore, we will define the following set. F will just be the set of all the finite sequences of pn's, so these are positive integers, and p1 shall be smaller than p2, and that shall be smaller than p3, and on and on and on, up until pm, and importantly, m should be greater or equal to. Alright, and with this at our disposal, we can rewrite this norm as alpha n in the A norm is 1 over the square root of 2 times the supremum of the following set, the set of the z's of alpha pn, for which the pn's, where n goes from 1 to m, is an element of f. Okay, and now it doesn't look that much complicated anymore. Before we think about this in a more intuitive way, first some remarks. This abbreviation I did in a different way in my original thesis. And in my original thesis, this was the first definition, 3.1. However, I decided to go about this a bit differently for this lecture series, also because my advisor didn't really understand or like the way I did it in my thesis. Not that it was incorrect, but I guess it was a matter of taste. And I also think that in this way, it looks much more mathematically elegant. However, I am very lazy, and in fact too lazy even, to renumber the definitions in my script from my thesis. So even though this is the first definition of this chapter, I will now call this definition 3.2, and there will be no 3.1, because, as I said originally, this was 3.1, but now I go about this in a different way. Okay, and don't worry, we will very soon go over this imposing norm in an intuitive way. First, however, I will also define this alternative norm, with which we will denote with a small b down here, and it will look very similar to the other norm. However, here we will not take these z's, for we will drop this part right here. This will fall away. So we only have alpha pn minus alpha pn plus 1 squared, and then all of that in the square root, but we still take all of these finite subsequences right here. Okay. Now let's move on to understanding this norm. So what do we do up here? What do we do here? Well, these Z alpha PNs are the first thing to wrap our minds around. So what are these Z alpha PNs? Well, we take a finite subsequence of our alpha n's. So maybe here we have our alpha P1. And then here we will have our alpha P2. And then here alpha P3, and so on and so on. I write this in a suggestive way. You will soon see why. So these are just, this is just our finite subsequence. And then we add in this sum right here of our z's, here we add the differences of these alpha pn's and alpha pn plus 1s. And then at the very end, we add alpha pm minus alpha p1. So this is the difference of the first and the last element of our finite subsequence. So this will go to our alpha pm here, and we just add all these differences here. That's one of those Z alpha PMs. It's the square summation of all these differences. Okay, think about that for a second. And then we take the supremum over the set of these Z's, right? Right here. So we take more and more finite subsequences to kind of push this value that these Z's can achieve to its limit. We push this up to the supremum. And then at the very end, this is not very complicated, we just scale it by the factor 1 over square root of 2, for reasons that will become apparent later. So this is a way to think about the space, or about the norm of James space. So a nice example would be example 3.3. First, the standard basis vectors, so the standard basis vectors En, which I hope you remember from the very first chapter, are all elements of J. And you can think about this very easily in the sense of our little image here, because, well, these ENs, let this be EI, it has the form 0, 0, and so on and so on. Then you have 1, 1, and then only zeros after again. So these finite subsequences that we take, if we don't have only zeros, will look somewhat like this. Here we go back to the beginning. We have this cyclical summation. And obviously, the only way for this to have any value at all is to sum this difference, which will be 1, and this difference, which will be 1. And if you calculate this, you will actually get also that the norms of these ENs are all 1. And this is why it's important to have this 1 over square root of 2 at the very beginning of the definition. Because if that would not be there, then these basis vectors would not be normalized. You verify this mathematically yourself if you want. All you have to do is consider different cases, like if we only have zeros in this subsequence, or if the 1 is at the very end or very beginning, and stuff like that. You will figure it out. And something more interesting would maybe be a sequence that is in C0 but not in J. And for that, consider beta n, where beta has the following form. We have a 0, and then 1 over square root of 2, 0, 1 over square root of 3, 0, 1 over square root of 4, 0, and so on. You then have a 1 over square root of 5, 1 over square root of 6, and so on and so on. Clearly, beta n is an element of C0, right? And it is not in J, however. And why isn't that? Because if we take P1 up to Pm in the following way, Pn will just be n for all n element 1 to m. And we do this with m being a odd number. So this shall be a odd number. Then we have that z of beta Pn squared, which is the sum of this form, beta Pn minus beta Pn plus 1 squared plus beta Pm minus beta P1 squared, is of the following form. This is just 0, and the rest, well, we have 0 minus 1 over square root of 2, and then we have 1 over square root of 2 minus 0 squared, plus 0 minus 1 over square root of 3 squared, plus 1 over square root of 3 minus 0 squared, and so on, up until we get 0 minus 1 over square root of k squared, plus 1 over square root of k minus 0 squared, and this is just 1/2 plus 1/2 plus 1/3 plus 1/3, and so on, plus 1 over k plus 1 over k. And this is obviously, in the short notation, 2 times this sum right here. And for k going to infinity, this diverges. So the supremum is infinite, the supremum over all these z's is infinite, and thus the norm of beta n, the a norm of beta n, is infinite. And beta n is not in J. Okay, that was a nice example. And we now get to our first proposition. Proposition 3.4, which is the following, that the norms A and B are indeed norms and equivalent. Okay. For the proof that alpha n and beta n be elements of C0. And let Pn be some of these indices. Then we set alpha tilde n to be alpha Pn minus alpha Pn plus 1 for n in between 1 and m minus 1. We define it to be alpha Pm minus alpha P1 for n equal to m, and 0 for n bigger than m. Okay, and we define beta tilde n in the same way. Why do we do this? We do this to use the properties of the 2 norm from L2 to prove the triangle inequality for the A norm. So we have zeta of alpha Pn plus beta Pn. This is the same as the infinite sum, the not infinite sum, this sum of alpha Pn plus beta Pn minus alpha Pn plus 1 plus beta Pn plus 1, this squared, plus alpha Pm plus beta Pm minus alpha P1 plus beta P1 squared, and then all of that in the square root. Okay, now if this is not detailed enough, I am very sorry, but you can calculate this. This is the sum from 1 to m minus 1 of alpha tilde n plus beta tilde n squared plus alpha m tilde plus beta m tilde squared. And that all in the square root. Now, because we defined it to be 0 for n bigger than m, this is the same as the infinite sum. Now it's really an infinite sum of alpha n tilde plus beta tilde n. Right. Okay. And this is nothing but the 2 norm of alpha n tilde plus beta n tilde. These are sequences. This is the 2 norm. And then we apply the triangle inequality of the 2 norm. So we have alpha n tilde 2 plus beta tilde n 2. And this is actually nothing but z of alpha Pn plus z of beta Pn. Okay, and in total, we will now get the triangle inequality for the A norm. So in total, we have that the norm of alpha n plus beta n in the A norm is the same as 1 over square root of 2 times the supremum of z alpha Pn plus beta Pn, and Pn go through f. This is less than or equal to 1 over square root of 2 of the supremum of z alpha Pn plus z beta Pn, and Pn goes through f. And this is then less than or equal to the norm of alpha n plus the norm of beta n. Nice. So we have the triangle inequality. The norm is subadditive, and it is also absolutely homogeneous, because if we look at z of lambda alpha Pn, and we will add a square here, this is the same as this sum right here. We have alpha Pn, lambda alpha Pn minus lambda alpha Pn plus 1 squared plus lambda alpha Pm minus lambda alpha P1 squared. Okay, and you can pull out this lambda squared. We get lambda squared z of alpha Pn squared. So it's absolutely homogeneous. So now for the positive definiteness, obviously the 0 sequence has norm 0, and the other way is also true, because for alpha n not the zero vector in C0, we have that there exists a integer n, I in n, such that alpha I is not equal to 0. And we find a j which is bigger than I, such that alpha j is smaller in the absolute value than alpha I, because it's a zero sequence. Then for P1 equal to I and P2 equal to j, we have that P1, P2 is an element of F, and as such, we have that z of alpha Pn is greater than 0, and so the norm is greater than 0. And so the norm is actually a norm, because it's absolutely homogeneous, positive definite, and is subadditive. So we have that this is a norm. And the same argument goes for the B norm. It's really the same argument. I will not go over the details here. You can do it yourself if you want. And the only modification that you really need is in this argument up here. You should set this to 0 for n equal to m. And then it should work just fine. The rest should be pretty much the same. So these are both norms. But that's not all that we wanted to show. We also wanted to show that these norms are equivalent. So first notice that the norm of any sequence, the B norm of any sequence, is always less than or equal the A norm of any sequence. And why is that? That's because alpha Pm minus alpha P1 squared is always greater than or equal to 0. And furthermore, we see that z of alpha Pn, this is less than or equal to, now we pretty much implicitly again use the argument from before to use the properties of the L2 norm. This should just be by now a well-known inequality, whatever. This is the same, or this z alpha Pn is less than the following. We break this up like this. So here we have alpha Pm minus alpha P1 squared, and also the square root again. And this and this will both be less than or equal to the square root of 2 times the B norm of alpha n. And yeah, the same goes for this. And why is that? Well, that's because for Q1 equal to P1 and Q2 equal to Pm, we have that Q1, Q2 is an element of F. So the term alpha Pm minus alpha P1 squared square root contributes to the supremum calculated by or in the B norm. So in total, we have that the B norm is less than or equal to the A norm, and this is less than or equal to 2 times the square root of 2 times the B norm again. So the norms are indeed equivalent. Okay, but we are here in Banach space theory, so as you expected, J is a Banach space, and that will be proposition 3.5, that J with the A norm is a Banach space, a real Banach space. And for the proof, first we want to notice the following, that for any alpha n in J and m and n positive integers, we have that the difference of alpha n and alpha m Well, this is just the same as 1/2 times 2 times the difference of alpha n minus alpha m squared, and then again the square root. We did nothing here. And this is 1 over the square root of 2 alpha n minus alpha m squared square root. And this is the same as 1 over square root of 2 of alpha n minus alpha m squared plus alpha m minus alpha n squared square root, which is less than or equal to the a norm of alpha n. And with letting m tend towards infinity, we see that the absolute value of alpha n for a fixed n, this is less than or equal to the norm of the whole sequence. And now, to show that it's complete, we will again consider a Cauchy sequence in J, which will again be a sequence of sequences. So let now beta nj, again with the double index, nj be a sequence in J. And it should be Cauchy, so a norm Cauchy sequence. Okay, obviously, for all epsilon greater than 0, there exists a j epsilon in the natural numbers, such that for all j and j dash, which are greater or equal to j epsilon, we have that the difference in the a norm of beta nj minus beta nj dash is less than epsilon. And with the previous inequality, we immediately see that the difference of beta n0j minus beta n0j dash is always less than epsilon for all fixed n0 from the natural numbers. Now this means that beta n0j is a R-Cauchy sequence, and thus it converges, so the limit as j goes to infinity of beta nj exists, and we will call this gamma n. So gamma n is now the sequence of limits of the elements at the same place in the different sequences that this sequence of sequences is made out of. Okay, I hope you could follow that. Now let epsilon be greater than 0 and j epsilon be an element from the natural numbers as before. And we fix j and j dash greater than j epsilon. Okay, and now we take Pn, n goes from 1 to m, a index sequence from F, and then, here it comes, 1 over the square root of 2 times this sum right here. We have beta p n j minus beta p n j dash minus beta p n plus 1 j minus beta p n plus 1 j dash squared plus beta p m j minus beta p m j dash minus beta p 1 j minus beta p 1 j dash squared, and this all in the square root. Oh, this is so horrible, but this is less than or equal to the norm of beta n j n minus beta n j dash n in the A norm, and thus it is less than epsilon. And why is this so important? For j dash tending to infinity, we now get that 1 over the square root of 2 times this sum right here, but now we have beta p n j minus gamma n, because gamma pn, because this is the sequence of limits, right? Minus beta p n plus 1 j minus gamma p n plus 1 squared plus beta p m j minus gamma p m minus beta p1 j minus gamma p1 squared square root. This is less than or equal to epsilon. And finally we see thus that the entire norm of beta n j, this is a sequence in n, minus gamma n, in the A norm this is just less than or equal to epsilon. And what does this mean? This means that beta nj converges to gamma n for j going to infinity, which is great. And we can also verify via triangle inequality. Now I will already stop the video here, because in the next video we will prove the most important theorem of this whole lecture, which is that James space actually has a monotone and shrinking Schauder basis. And this will allow us to apply everything that we have learned so far. I hope you are as excited as I am, and I will see you then in the next video. Bye bye.